So thank you for the invitation here. So I'm very happy to talk. The subject of my conference is nicely connected, you will see, to this idea of a Lie-Størmer center, because I would essentially speak about Lie calculus, very classical Lie calculus actually, and very classical problems related to Lie calculus, and also connected with some applications or possible applications to numerical analysis. So in that sense, it fits the project. So this is based on a joint work with Adrian Celestino, which is at the moment at NTNU in Trondheim. And it's also connected more generally to a project we have with Kourouche Ibrahimi-Fa to develop a sort of new chapter of group theory. I will make some allusions to it. I won't develop too much this aspect, but the idea is to extend the classical Lie calculus in a direction and that I will indicate during the talk. So very briefly, the remark on the terminology. I won't explain these things in detail, but the terminology forest formula, it comes from quantum field theory essentially. There's a formula there related to a subject, a topic we mentioned already today, which is renormalization. And so in high energy physics, when you want to remove infinities, there's a process which is group theoretical, and where you have to compute an inverse in a group. And this inverse is computed using what is called the forest formula, because it's parameterized by a forest of subgraphs of a given Feynman graph, or a family of Feynman graphs. And so this is where forest formulas have appeared. I worked some years ago with Frédéric Magnus on this problem, and we managed to understand that this Zimmermann forest formula was actually a particular case of a general formula that can be obtained for group inverse in off algebras, which are called antipodes. So the antipodes in a family of off algebra, which is say the point of view of functions of groups with respect to the computation of the inverse. So we managed to prove that this Zimmermann forest formula had a much general formulation, and the idea of the talk today is essentially to show that this kind of strategy applies also to other problems, and I will focus mostly on the Magnus problem that I will explain later. So the precise motivation of our work with Adrian was a bit different. Namely, we started from a problem in free probability. So I will start to explain a bit the corresponding framework, show you how things are organized, what are the problems that appear, and how it leads to this idea of using forest formula to solve a certain combinatorial problem. So I will first recall very briefly some very classical ideas in probability, but they're going to be important for what I'm going to explain later. In classical probability, the independence of random variables is encoded usually by this kind of identity. So you have the expectation value of the product of a function of a first random variable and a function of a second variable, and if you can decompose this expectation of a product as a product of expectations, then the two random variables are independent. This is the classical formulation for the independency of two random variables, and it extends to the notion of independency of subalgebras of a given algebra of random variable. So the point I want to insist on is the notion of cumulant, namely, and this is not always well known, a good way to encode the independence of random variables is by means of cumulants. Cumulants are defined that way. If you look at the exponential generating series of momenta, so the expectation value of the powers of a random variable, and you take the corresponding exponential generating series, the exponential generating series of cumulants is defined as the logarithm of the exponential generating series of momenta. And if you come back to the definition of independence, you see that the independence of two random variables x and y translates in the fact that the generating series of cumulants associated to the sum is the sum of the generating series of cumulants. So in a certain sense, cumulants linearize independence. And this is a phenomenon that is going to happen also in other theories I will mention in the next slides. Namely, this property of linearization of independence is going to hold.
Non-independence, wait, I don't understand. What does that mean? Oh, I see, because it's a product, it's non-linear. I don't understand what that means.
Well, linearization means precisely this, namely that if you have the exponential generating series of the sum of two random variables, then if it decomposes that way, if it decomposes linearly, then it means that they are independent. So it's a way of coding algebraically independence. As you will see later, there's a sort of theoretical interpretation of this. Namely, there's a way to make sense of the fact that the exponential generating series of momenta is group-like in a certain sense, whereas the exponential generating series of cumulants is of Lie type in a certain sense, which means that this is really a group Lie duality which is there implicitly, although it's not obvious.
The meaning is if cumulants are non-zero, then if it's non-linear, the cumulants are non-linear, then the variables are dependent.
Yes, exactly.
Right, I mean, I'm trying to understand the phrase.
Yes, yeah.
The meaning. Okay.
So the idea is that the linear behavior of cumulants is a way to they behave linearly when you are applying the computation to independent random variables, as it's going to fail.
The English sentence should be cumulants linear implies independence.
Yes, but this is a sort of
if and only if.
this is a sort of
Characterizes independence.
yes, exactly,
Linear characterizes.
exactly.
Okay.
Mm.
It's even only.
What?
It's even only, is it?
Yeah.
I mean, this expression, cumulants linear as independence, is with this, yes, precisely to indicate that it's a sort of a way of expressing the meaning of the, informally the meaning of the
So
precise mathematical. Yeah.
It's
Yes.
if and only if.
Yes,
Right?
exactly.
Is that if and only if?
Yes, essentially, up to details, like the fact that you have to have random variables with momenta at all orders, things, small analytic details like this. But the idea is that, anyway, x and y are independent implies that this formula is true, namely that you can move from a linear combination of random variables. You can expand this at the level of exponential generating series linearly. Well, everything is there. So that's the first way to speak about cumulants in terms of exponential generating series. There's another way to relate momenta and cumulants, which is by means of the combinatorics of set partitions. Namely, you can define cumulants by this formula. So if you expand the momentum of order n of x as a sum of these terms, where I use this notation. So if I have a partition pi with components p1 to pk, this term is the product of the cumulants indexed by the number of elements in each block p1 to pk. So this expression is equivalent to the previous one by means of exponential generating series. And then there's a third way to encode the relation between momenta and cumulants, which is this one. It's more algebraic and it's related to central limit theorems. So if you have three random variables, x1, x2, and x3, and you duplicate them, so you create for each of them an independent copy, a copy in an independent algebra of random variables, and you expand the expectation of the product of this linear combination. So the product of linear combinations of x1 with x prime 1 and so on. What you get is, of course, of this form, because you have assumed that they are independent, x1 and x prime 1 and so on. And the pattern of the formula you have this is related to the unshuffling of words. So if you think of what happens in terms of words, you're starting from x1 to x3, you get one copy of this term, another copy of this term with dots, and then the other terms are obtained by selecting in the word x1, x2, x3 a subword, and then taking the complementary word that you put on the other side. So this last formulation of independence points out in a different direction than the two other ones. Namely, it relates to the combinatorics of shuffles and shuffle of words and unshuffling of words. So that's not exactly what I want to speak about. I want to speak about the extension of the theory of probability when you move from algebras of scalar random variables to algebras of so non-commutative algebras of random variables, which are defined that way. So a non-commutative probability space is an associative algebra equipped with a linear form that is required to be unital, so to map the unit of A to the unit of the ground field, which I've taken to be complex numbers here. The analog of momenta in this setting is given by so this linear form applied to the powers of the elements of A. And the nice thing when you move from
Some notion of positivity required?
it depends of what you're doing. For what I'm doing, not. But if you move to C-star algebras, and then you will have some conditions of positivity. But I don't require it. It really depends of what you want to do. But in that case, I don't insist on positivity because I don't need it for all this part of non-commutative probability or quantum probability. You don't have to appeal to positivity. So the point is that when you move from commutative to non-commutative, there are several theories which are possible. Whereas in the commutative case, there's just essentially one probability theory which can be obtained requiring certain naturality property. So this has been done by Schurman, Speicher, and others. So they classified the reasonable non-commutative probability theories that exist, and they managed to prove that there are essentially four possible theories. So tensor probabilities, which are just the extension of the classical theory of probability to the case of operators or associative algebras. And then there are three new theories that appear, whose combinatorics is different than the one of classical probability and tensor probability. They are called respectively free, Boolean, and monotone probabilities. And they can be studied by following three approaches, which are reflecting the three I have mentioned in the classical case. Namely, you can start from the point of view of generating series, and then the techniques you will use are closely related to analytic combinatorics. This point of view was developed by Voculescu and other people after him. There's a second point of view that reflects the second definition I gave of, or implicit definition I gave of cumulants, which relies on the combinatorics of certain lattices, and this was developed by Speicher and then other people. And there's a third approach, which is purely algebraic, which is closely related to the notion of shuffles that I recalled in the, whose appearance I recalled in the classical case. So the notion of shuffle has to be extended. It's not exactly the one I described. But anyway, there's a purely algebraic approach to non-commutative probability that we developed for about 10 years with Kouroush Ibrahimi Farr. And this approach is going to underlie many of the constructions I'm going to discuss later. So to skip time, I will run directly to this picture. So the interesting object when you're moving from classical to non-commutative probability, and precisely to these three theories, so free, Boolean, and monotone probability. The interesting objects from a combinatorial point of view are the non-crossing partitions. So non-crossing partitions are partitions of sets of integers that you can represent that way. So without crossing of the components associated to the blocks. And
I didn't understand what NC again is.
so this is the set of non-crossing partition.
Yeah, what does that mean?
So a non-crossing partition, so it's a partition, but where you ask a condition on the blocks, namely you don't want to have A and C in one block and B and D in another block. You don't want this kind of situation appearing. So this is encoded graphically by this kind of picture. So a bit of terminology. So these are the non-crossing partitions. A non-crossing partition is irreducible if the first element in of the set of integers you partition and the last element are in the same block. So this is an irreducible partition. Boolean partitions correspond to the case where in each block you have only successive integers. So you cut into, in a certain sense, combinatorially connected pieces, your set of integers. This is an irreducible component of a partition. This is another one. And the last point I want to mention concerning terminology is the fact that to each non-crossing partition like this, you can associate a tree by looking at the order, the implicit ordering of blocks when you move from top to bottom. So in that case, you have a top component 1 that you put as the root of a tree. You have component 2. You have this block that is going to give rise to this node, this vertex of the tree, and 6 is going to the bottom of the tree, which is represented upside down and so on. So this gives the, I don't want to enter too much into details, but this gives the rule, the way you associate to a non-crossing partition a tree. And this is going to be important for some things I'm going to say later. So another notation, if we have if we have a function from a to the n to c, I will use this notation, and a partition pi, I will use this notation. So f indexed by pi means that I'm going to take the product of f evaluated on the subsets that correspond to the blocks. So if I have a block composed of A1, A5, and A8, I would have in the right-hand side f evaluated on these three letters. And I make the product over all blocks to define f of pi. So this is just a notation, but it's important for making sense of these formulas. These formulas are the analog for free probability of the formulas relating momenta to cumulants in classical probability. If you remember the formula I gave, so the expectation of the power of a random variable was associated to a certain sum over all partitions of the corresponding set of integers. So xn would correspond to the decomposition will be indexed by all partitions of a set with n elements. Here instead the sum is over all non-crossing partition of n, the set of the first n elements. So this defines the notion of cumulant in free probability, and as you can guess from what I explained at the beginning, if you have a good notion of cumulant, you have a good notion of independence, and essentially it characterizes the theory of probability you are going to handle. So this essentially defines free probability. This definition, where I'm looking now just at interval partitions, defines what is called Boolean probability, and there's a third theory which is slightly different. So this is the set of Boolean partitions or interval partitions, where you decompose a set of n elements into blocks where all elements are following each other in each block. So Boolean partitions I discussed earlier. And so there's a third theory which is slightly different from the previous one, which is called monotone. The definition is the same as free probability, but with some coefficients where combinatorial coefficient, which is called the 3 factorial, is appearing. So this is the factorial associated to the 3, associated to a non-crossing partition that is appearing here. I don't want to define it, but this is a simple and standard definition in combinatorics. So the question that has arisen interest in among people doing non-commutative probability was to relate these various theories. And so to relate these various theories, you may want to relate the notion of cumulants, because they really encode the fundamental properties of the probability theories you're considering. And so Arizmendi, Azebe, Lehner, and Vargas managed to obtain closed formula relating the various theories. So the formulas themselves are not very important. The important point may be to signal is that the combinatorial coefficients that appear in the formula are the 3 factorials again. But in this combinatorial approach to non-commutative probability, some connections were missing that we managed to obtain recently. So the paper was published in 2021. So this is a joint work with Celestino, Ibrahimi Far, and Perales. And we obtained formulas expressing monotone cumulants in terms of Boolean cumulants and free cumulants. And the only point on which I want to insist here is the fact that new coefficients appear in these formulas. And these coefficients actually were not new, because they had appeared earlier in the work of Murua in numerical analysis. So technically, these coefficients are defined that way. If you have a non-planar rooted tree with t vertices, then the coefficient is defined that way, where omega indexed by k is the number of surjective strictly order preserving map from the tree to the set of the first k integers. And the interesting point is this coefficient, which is of logarithmic type, and we will see actually that one reason why the coefficient has this shape is precisely because there are some logarithm computation involved, or possibly involved in the obtention of the formulas we got. So, in what context did Murua obtain this formula? He obtained the formula in studying the Backel-Cambersdorff problem. The Backel-Cambersdorff problem is so one of the basic problems in Lie theory, and one of the most fundamental ones, because it's essentially the solution to the problems gives a way to transport the product law, or formally at least, the formal law, product law on a Lie group to the tangent space at the identity, so to the Lie algebra. And there are various other formulations of the Backel-Cambersdorff problem. And so Murua was interested in the Backel-Cambersdorff problem, facing a difficult problem, namely when you compute the logarithm of a product of exponentials, you know that it's going to live in the free Lie algebra over the variable x1 to xn. There are several ways to obtain expression for this term. But if you want to have something numerically as efficient as possible, you want to express this in a basis of the free Lie algebra. So the theory of basis of free Lie algebra is the theory of all bases. And Murua was, the purpose of the paper was to obtain formulas in all bases for the solution to the Backel-Cambersdorff problem. So it's one of the relations of the talk to Lie theory. So what we wanted to do is first to understand, to give a theoretical reason why these coefficients were appearing. Maybe make a connection with the Backel-Cambersdorff problem, and then progressively we move from this initial project to the project of of embedding this kind of calculations, so in relation to the Baker-Campbell-Hausdorff problem and in relation to free probability, to the broader setting of obtaining formulas in the theory of Pauli algebras, which I'm going to define later. So let me move to Pauli algebras. I need to recall something about polynomial algebras. When you start from a vector space B and you look at the algebra of polynomials over V, you can introduce the dual structure, so coalgebra structure, a map from K of V to the tensor product of K of V with itself, which is defined that way. This is the dual notion of the product on the polynomial algebra. So introducing the coproduct makes the algebra of polynomial with the usual product and this new coproduct of algebra. So concretely, for those of you who don't know what of algebra is, it means that this coproduct map from K of V to K of V tensor K of V is a map of unital algebras from K of V to its tensor product with itself. And when defining of algebra, there's a notion of antipode which reflects at this level the notion of inverse in groups. It's not really essential for what I'm going to say because the kind of algebras I'm going to consider always have an antipode, so I won't insist on antipodes. And I don't do it either now. So what is a Pauli algebra? A Pauli algebra is a vector space equipped with a linear map from L tensor L to L, so a bilinear map, which satisfies this property. If you look at the associator for this product, this triangle product, for the elements U, V, and W, so you look at the associator, you exchange W and V, you look at the associator for U, W, and V, you want the identity of the two associators. So if this identity holds, you have a Pauli algebra, and it's called Pauli because if you antisymmetrize this Pauli product, you get a classical Lie bracket. So this is one possible connection with the question that was asked at the end of the previous talk. So the reason why Pauli algebras are important and appear everywhere, one of the reasons is that they are closely related to the notion of bracket of vector fields. So as you know, you can define the bracket of two vector fields in the usual way, but there's a different way to do it, which is to apply the differential operator associated to a vector field Ax to the components of the other vector field. So this defines a new product, and this new product defines a Pauli algebra structure on vector fields. And if you antisymmetrize this product, you get a Pauli product. So that's one of the most natural appearances of Pauli products, and a reason why they appear very naturally in particular in numerical analysis, but also geometry, group theory, and many other places. So the general philosophy behind what I'm saying is that it's natural to try to enrich the classical group theory in the and the classical Lie theory in the direction of Pauli algebras, and to mimic all the constructions as far as possible that have been done for Lie algebras in this extended framework. So technically, the very important point for what I'm going to explain, I will have to run because so I'm late on the slides. Probably I wanted to say too many things, but if you have a Pauli algebra, it's in particular a Lie algebra because there's this forgetful functor from Pauli algebras to Lie algebras, and so you can define its enveloping algebra. So usually there's a standard way to do the construction of the enveloping algebra, but in the particular case of Pauli algebra, you can give a very specific form to the enveloping algebra. Namely, you can choose the algebra of polynomials over L, with the coproduct I've introduced earlier, which is the coproduct which is dual to the product of polynomials. But you can define a new product, a new associative product on the algebra of polynomials over L using this formula. So you want to define the product of two monomials, an associative product of two monomials. You're going to split this monomial B1 to Bm in all possible ways as a product of monomials B0, B1 to Bl. So you do this in all possible ways. And to make sense of the right-hand side of the equality, you have to define what are these expressions A1 brace B1. And this is done in the following way. So this is a recursive definition. You define the brace product of V and W to be the Pauli product of V and W. And this is extended recursively to expressions with higher order monomials or higher order sequences of terms in the braces. So if you do so, you're going to equip the algebra of polynomials over your Pauli algebra with the Hopf algebra structure. But and so this dualizes to Hopf algebra structure on the dual. But the nice thing after you've done this is that now you have two Hopf algebra structures on the same polynomial algebra. So one that is coming from the product of polynomials, one that is coming from the associative product that describes the enveloping algebra structure of the Pauli algebra. So since you have these two structures, you can play on this joint existence of two products, and in particular you can define logarithms and exponentials for the two products. All these constructions are on graded structures, so these operations are well defined. And in particular, when you move from the Lie algebra to the group, so this is standard in Hopf algebra, you can move from or in enveloping algebras, you can move from the Lie algebra to a group that is associated to the completion of the enveloping algebra using the exponential map, and you can go from the group to the Lie algebra by the logarithm. So this formalizes the classical link between Lie groups and the algebras in algebraic terms. And if you do this using the two products, so defining these two logarithms and these two exponentials, you will be able to get two automorphisms of the Pauli algebra you're starting with, or its completion with respect to the graduation. Namely, you can compose the logarithm associated to the commutative product with the exponential associated to the associative product, or conversely, you can compose the logarithm associated to the associative product with the exponential associated to the commutative one. And if you do so, you obtain two automorphisms, and it happens so that they coincide with two morphisms that were first defined, I think, by Agrachev and Gamkrelidze. They were studied also by Ibrahimov and Manchon later, which are called respectively the Pauli exponential and the Magnus operator. I will return on them later on. So now I would skip this, the explanation of this formula, but just give its meaning.
What does locally finite dimensional mean?
So these objects are graded, and locally finite means that it's finite dimensional in each component. So when you have an enveloping algebra, there's a canonical projection from the enveloping algebra to the Lie algebra for at least when objects are graded for abstract nonsense reasons. And it happens so this is encoded by an operation that was defined by for the first time by Solomon. And this projection from the enveloping algebra to the Lie algebra takes a particular form in the case of the enveloping algebra of pre-Lie algebras, precisely because the enveloping of algebra can be represented as an algebra of polynomials. So you have a precise form for this projection operation, and it allows to give a sort of simplified or more precise expression for the Magnus operator that I've defined earlier, in terms of the composition of the commutative exponential with the associative logarithm. So this is one expression that is going to be very useful later. Why is this operation omega called the Magnus operator? It comes from one solution to the continuous Backel-Campbell-Hausdorff problem. So the computation of the logarithm of the solution of matrix valued differential equation, which is given by this formula. And the connection with Pre-Lie theory comes from the fact that when you have time-dependent operators or time-dependent matrices that you normalize properly, if you define this operation, it defines a Pre-Lie product. So this allows to rephrase the classical formulation of the Magnus solution to the Backel-Campbell-Hausdorff problem in terms of Pre-Lie algebras. So that's the connection of what I've explained to the Backel-Campbell-Hausdorff formula and the theory of links between Lie algebras and Lie groups. And there's another appearance of Pre-Lie theory in connection to what I explained at the beginning, which is related to the fact that Pre-Lie structures also appear in free probability. So this is results we obtained with Kouroush, Ebrahimi Far some years ago. And namely the fact that there's a way to understand the relations between the various notions of cumulants appearing in free probability in terms of the Pre-Lie exponential and the inverse Magnus operator. The underlying Pre-Lie structure is formally the following one. It's relatively connected to the previous talk. That's why there could have been connection between the two, but it seems it's not the case. So if you start now from a finite alphabet and you look at words over the alphabet and linear combinations of words over this alphabet, you can define a Pre-Lie product in the following way. If you have two words, you can insert gamma inside alpha in all possible ways. The only thing you want is that when you look at the possible insertions of of gamma into alpha, when you cut the word alpha into two pieces, you don't want these two pieces to be, one of these two pieces to be empty. So this defines a Pre-Lie structure. It's easy to check. And so the structure is combinatorial, and it's relatively easy to write closed formulas for all the expressions you can obtain. So for example, if you want to compute the brace operations I've defined recursively earlier in this setting, you obtain this formula where you're going to insert gamma 1 and gamma n in all possible ways inside alpha, modulo the fact that you want alpha 1, so the first component of alpha you put to the left and the last component you put to the right to be non-empty. And else you just plugging in all these words, gamma 1 and gamma 2 till gamma n in all possible ways inside alpha. So so this defines the Pre-Lie structure, which is naturally appearing in free probability. So as a conclusion, I would like to connect everything and explain how you can compute this kind of formulas explicitly in basis of a Pre-Lie algebra. And the way we're going to compute such expressions is by using duality. So by using a dual basis and computing the evaluation of terms like this one. Using duality means that we are going to translate the product on the left-hand side, so typically the iterated product with itself of a given element of the Pre-Lie algebra. We're going to use duality to compute these expressions. Using duality means that we are going to use iterations of the coproduct on the dual of algebra of the algebra of polynomials over L equipped with the enveloping algebra coming from the polystructure of L. So
So how do you put the parentheses in the next term?
Sorry?
How do you put the parentheses in the next term?
You always put the parentheses up on the left.
Oh,
So it's indicated that way. So you're going to put a parenthesis here and then take a bracket to the right. So that's a non-commutative exponential. So you have to choose the order, and you put always you always start from the left to iterate. It's not completely obvious that these formulas correspond to the formula I've given in terms of compositions of logarithms and exponential, but it is true. You have to prove it, but it is true. So now the last key point I wanted to explain is what happens if you move to the dual of algebra of the enveloping algebra of L. What happens is that so it's a polynomial of algebra, and terms are monomials. And if you look at what happens when you compute the coproduct of an element in the dual, choosing a basis. So now I'm working in a basis. I want to have effective formulas. Well, this coproduct will be associated to structural coefficients. So its structural coefficients in the basis, with this specific form in this case, that the left term with respect to the tensor product is going to be linear. If I start from an element in the dual of L, I will have here an element in the dual of L, and here I will have all possible monomials over the dual of L. Which means that I can represent graphically, and this is going to be the link with Forest formulas. I can represent generically this coproduct as a sum involving the structural coefficients of the coalgebra and a graphical encoding of these terms that at first order is given by corollas. So trees with with a root and a sequence of vertices directly attached to the root. Now, if I iterate the coproduct, so for example, if I iterate the coproduct at the level of E1, I will get a tree now of depth 2. If I iterate the coproduct instead on simultaneously on I1 and I2, I will get trees of these forms. And in general, I will get, when iterating in all possible ways coproducts, I will get terms associated to trees decorated by pairs of positive integers corresponding to the application, the iterative applications of the coproducts, and leaves decorated also by pairs, because for consistency I'm choosing to duplicate the integers appearing in the recursive formulas. So when I have such a tree, I can attach to it a certain coefficient, lambda t, that I won't define, but the definition of this coefficient combines two things. It combines the structural constants of the Pauli algebra associated to the coproduct, and certain symmetric coefficients, because we have trees and one has to take care of possible multiplicities. So anyway, it's possible to define to associate to each tree a coefficient lambda t. And now I'm able to come back to Mura coefficients. If you remember the definition I gave earlier, if I have a tree, or more generally a finite poset of a given cardinality, I can look at its linearization. So surjective map to sets of.
Besides the pre-Lie algebra, what else do you need to get the coefficients?
Sorry?
Besides the pre-Lie algebra, what else do you need to get the coefficients?
Nothing. These coefficients, there are the coefficients lambda t. Their definitions involves the structure constant of the Pauli algebra and the shape of the tree. So looking at the shape of the tree, what happens is that certain subtrees can be repeated, and you have to take into account carefully the way these multiplicities appear to define the coefficient lambda t. But they are purely combinatorial. They just follow from the shape of the tree. They don't involve anymore the structural coefficients of the Pauli algebra. So I have now this notion of calinearization of a poset. So this corresponds to surjective maps to the set of the first integers, the first k integers, if I look at calinearizations. And now, when I have a linearization of a tree T, I define this tensor product C of f as a certain product, as a certain tensor product of monomials in the elements of the dual of the Pauli algebra, which are defined technically that way. So this corresponds to terms that are going to appear when I'm iterating the coproduct. So the point then is that if I want to express the iterated coproduct, so not exactly the iterated coproduct, but the reduced iterated coproduct, which means that I'm eliminating terms that contains tensor product that contains a copy of one somewhere. So if I'm looking at the iteration of the reduced coproduct acting on an element of the dual of the Pauli algebra, I can show that this iterated coproduct rewrites as a sum indexed by all trees, all the trees associated to bi when I'm iterating the coproduct. So technically, all the trees, all the decorated trees, such that the third decoration of the root is I. So I sum over all these trees and over all calinearizations of the trees. Then I have this coefficients lambda t. I have not defined, but I will roughly explain the way it is obtained, times this tensor product CF of elements in the Pauli algebra. So there's a way, a closed formula in terms of trees describing the iteration of the reduced coproduct, and it comes from the fact, this fact that essentially I can understand in terms of the construction of trees the application of the coproduct on the dual of the Pauli algebra. So now I can return. I'm sorry, I'm a bit late probably, yes.
Yeah,
I'm going to try to conclude. I can return to the formula I wrote at the beginning. So the formula expressing the Magnus operation acting on an element of my Pauli algebra alpha. If you remember, the key point was that the Murua coefficients were appearing. So now, if I put together all the explanations I've given, you see how you can do the computation. You do the computation by duality, so by looking at the action of omega alpha on the duality algebra. I know that I can compute this Magnus operator as the composition of the projection from the enveloping algebra to the Lie algebra composed with the commutative exponential in the algebra of polynomials over my Pauli algebra. I pair with the element omega I. But then I have all these phenomena that happen in enveloping algebra of Pauli algebra. So this allows me to give this first formula to avoid this term. This is related to the fact that this projection has a very specific form in the case of Pauli algebras. Then if I use the definition of the product in the enveloping algebra and the way it behaves with respect to the degrees of the left-hand side terms the product. What happens is that when I'm making these products iteratively, I'm always going to increase the powers appearing on the leftmost term, which means that since I'm pairing with something which is linear, I'm pairing with an element in the dual of the Lie algebra, this formula I've obtained simplifies. I can keep only the terms where the first power is 1. Now if I use duality, I rewrite this pairing using the iterated coproduct acting on the term omega I. And if I use the fact that I can interpret iterated reduced coproduct acting on the dual in terms of trees and linearization of trees up to the introduction of certain coefficients, then I'm able to connect all these things and understand and recover actually the fact that the Moore coefficients have to appear in the computation of my terms omega alpha paired with omega I in all possible ways. So this explains in abstract terms or group theoretical terms or Lie algebraic terms, if you want, why these formulas are appearing when you try to solve the Backel-Kambalov problem, typically in the continuous case using Magnus approach. It also explains why we arrive to these terms when we try to compute the formulas relating the various families of cumulants in free probability, because at the very end this is always the same phenomenon that is appearing. There's a pre-Lie algebra structure. This pre-Lie algebra structure gives rise to a very specific form of the corresponding enveloping algebras of algebra, and using the properties of these enveloping algebras allow to derive methods that end up with also with closed formulas and explicit formulas for the in that case, well, in the case I've studied here and we have studied in the paper, so for the Pauli exponential and the Magnus operator, which has in a certain way the two fundamental operations in the framework of Pauli algebras, paralleling what exists for the classical Backel-Kambalov formulas in the theory of usual Lie groups and Lie algebras. Okay, I will finish with this. I'm sorry because I wanted to say too many things probably and skipping details, which was maybe not the best idea, but anyway, that was. I've tried to give you insight.